Okay, is this thing, let's see. Let's see.
I think if I walked it, I'd probably get up at like 2 in the morning or something. If I had to walk, I'd have to get up at like 2 in the morning and
Yeah.
Where did
start walking.
I downloaded the PowerPoint. Where did it go?
Probably in the bottom right hand corner.
If I was doing
bottom
a
left
nice
of the
job.
browser. There's probably still a pop-up there.
All right, thanks. Functioning, but right, so we're way somewhere. Right, so let's see. So I wanted to go through what there's a few things. Right, so there's this business on this is these bottle brush. A couple papers on bottle brush that I don't know. I think I used them for quizzes at some point. Let's see if this is going to work. Hopefully Zoom is working. Someone's on Zoom, right? Yeah, is whoever's on Zoom, is that working? Can you see Doc Cam?
Yeah, I can see the dot
Not
cam.
speaking. All right, I think it's, I put record, so it must be okay. Anyway, there's two papers. They both do Monte Carlo. And they both do coarse grain simulations, and they're both doing, so you have like beads. So one of them calls it NB, number of beads, main chain beads. And they put these side chains in, and one's, then there's like high density, low density of side chains. This is like polyethylene kind of, because when you get, you can put in a copolymer that has like a butene copolymer. It would give like, instead of ethylene, it's got an ethyl group on the side, and then that causes a chain to have these defects so that it'll crystallize only to that thickness, more or less. And so you can reduce the crystallinity and control the crystal size, which controls the melting point. Anyway, so they're just looking at chain persistence, so, and they're doing kind of the same thing, like calculating the this vector R at each point dotted with the overall chain R. And then do that for a bunch of different chains, find the average, and that gives them this normalized by the absolute value of R, gives them this persistence length. So then they map it versus position. So it's kind of the same thing as the other paper we got. And let's see. So yeah, so they get this kind of behavior. Let's see, this lambda here is the bending penalty, which is, where's the equation for that? It's basically that the bending penalty, the larger the bending, so it's going to be like the persistence length is L naught 1 plus something over this bending penalty. So for the K unit, this bending penalty number, they can just tune it to change the stiffness of the chain. So the larger that the stiffer the chain. So it must not be 1 over, it must just be proportional. So the stiffer the chain, the more the persistence. That's kind of the idea. So it, let's see, the persistence drops. Now, the larger that is, the more flexible the chain. It's just whatever I wrote there. So if that gets larger, then you go towards a small L0, and then the C infinity is this L persistence over the bond, so that drops as you increase it, increase the.
So larger persistent point is more flexible.
It's 1 over, this lambda is 1 over, right? It's 1 over lambda. Oh, sorry. Here, sorry about that. Wait, is that's projecting? No. Okay, that's all right. Okay. So it's 1 over lambda. So the larger the lambda, the smaller the persistence. And then it doesn't go to 0, though it goes to this L naught. Okay, so that would look like you have L naught. So this gets larger, that gets smaller, so it drops down like that kind of. Right. So if this gets really large, let's see, no. Anyway, the larger that is, the smaller the persistence. That's how it works. So he gets a larger lambda, it's a smaller persistence, and the C infinity or LP drops. Could be, you can plot C infinity or LP. And then when you get when it gets really stiff, I guess he has bigger end effects. I'm not sure why that is, but so anyway, that's one thing. So it's kind of like the behavior of it, how you can tune it. I linked these things. So that's this Conley paper. Put these links up here. This Conley's here. So it's this paper. I guess I thought I was going to kind of go through the his simulation method, but basically it's just bead and spring model, hard sphere. So they're totally excluding locally, and then they have this is the energy of the chain, so it's got R squared. This is the elasticity. That's like this is just an elasticity term, and that's a potential energy term for, and it potential energy is just on or off. Like when you get to the R greater than some cutoff size D, which is the sphere diameter, then there's no interaction. When so it's just hardcore spheres. That's what that thing means. Like if you get to smaller than D, then you have infinite repulsion, and then if it's a larger than D, there's no interaction. So that's like the simplest potential, hardcore sphere potential. And then their cone polymers is like high density and low density of branching, which those are the words you use for polyethylene. So it's kind of like modeling polyethylene a little bit. What else is he doing here? He calculates the rate of gyration. Anyway, in the end is whatever's in the so this paper, that's the Conley paper. There's another paper that's almost the same thing. Like he's also doing Monte Carlo polymer chains of hard spheres, NF side chains, NS branch points, NG. So his NB in the one is NG in this one. The backbone. Wait, no. NB is the backbone. That's NG. Separate. NG is the separation between the branches. All right. So anyway, so he's got his own nomenclature written up here. I think in both NB is the backbone though. So anyway, then they both do a Monte Carlo. So they let the thing take steps. So it's bonded so it can rotate. So the chains can rotate. So they let them rotate, and then they calculate the free energy. If the free energy drops, they accept the step. Free energy rises, then they have a temperature weighted choice whether they accept it or not. So if it's going to be flip a coin, whatever you come up with, there's a probability that's calculated with like so it's going to be a probability that's calculated with like you get some number that you get a random probability. that's your P star, say, and then there's a probability it's like an energy over KT exponential. So you set your temperature, and then you're gonna have the energy, like this will be the change, the delta E of the thing, and that'll give you another probability, which is gonna be less than 1. Then you compare those two, so it's temperature dependent. So the higher the temperature, the lower the probability of this thing, and that means the less chance that it's gonna happen. So, but it's random, it can happen. Right, so something bad can happen, but it's a lower probability the higher the temperature. The lower the temperature becomes high, then it can like phase separate or something, whatever you want it to happen. That's kind of the routine of the Monte Carlo. Anyway, so there's these two groups doing the same thing. They're a couple of years apart, right? Oops, that's one guy. This other guy, right? He's 2004. The other one's 2006. So anyway, so there's that business. So this is the Connolly one that he's from Ireland. So he's just showing that you get a higher persistence when you have a high density of branches, lower persistence when it's lower density. As you go along the chain, this is just that he's only doing, oh, this is as you increase the molecular weight of the chain. So when you have short chains, so short chains are going to have, so short chains, so if you have this kind of U-shaped thing with the persistence and then NB, if I have a short chain, so it's going to have more of this end effect thing. So it'll have a lower persistence. So as he increases the, so it kind of shows you how it behaves. So there's a problem with short chains, like they're going to have some oddball persistence length that you measure. As the chains get longer, you approach C infinity. That's one thing. He's got some power law for that. So this is kind of the way he models that. He says that the persistence length goes with this NB as a backbone to some power, right? Which is like kind of how you model everything that's kind of random. You just say it's a power law, right? So it kind of looks okay that he has that power. I mean, this is my plot of his data, but that's his function that he proposes. Then that's the simplest function. He proposes a more complicated function kind of for no reason. Both of these functions are for no reason. Like it's just like arbitrary. It looks like a power law. This is kind of arbitrary. That function might fit it, you know. So yeah, so it's kind of like that's true. Yeah, so it's like not enough to say this. It's a lot of parameters, you know. So anyway, and there's no, that isn't really the issue. Like the issue is that there's no logic, you know, behind it. It's okay to have a lot of parameters, some reason that you have them, you know. So, but if it's just arbitrary, it's kind of crazy. Okay, so one way you could look at this is like, you could say, well, all right. So if I have a chain and then it's got two ends, right, and it's got m molecular weight. So the probability of finding an end is 2 by m, right? So I could say that I have, the ends have a lower persistence. So I could have like 1 minus the probability of that times, or there could be another number here. And then your L naught, L infinity. So when that m gets infinite, then you get just L infinity and you have L persistence, right? So that'd be like, that's like the Flory-Fox equation for glass transition. It says like TG goes with TG infinity times 1 minus some number over the molecular weight. It's an N group effect. So when you get to high molecular weight, you get a lower glass transition. There's an oligomer glass transition is really low. Maybe it doesn't have one. And then as it becomes a polymer, So it's just N group effect. So it seemed like these plots, so that's like logic. That you would use something like that. So how does that work when you, he didn't do this, but oops. So this is LP versus 1 over N, which that would be that function. It doesn't work. I mean, you'd think that this would be like an in-group effect. It doesn't really follow that. You know, so it's kind of weird. So if you do, let's see, this is a different page. This is this guy Conley's paper, right? Where his NB is going up to 100. This guy goes to NB of 500. This Arun Yithra is at Wisconsin. He's like a chemistry department, Wisconsin. He's got a lot of papers. So anyway, if you do LP for Arun stuff, this is a second paper, 2006. It doesn't look that bad. Like that function kind of looks okay, except at the high NB end. So this is like 1 over. So this is the high molecular weight end over here. Right. So that function doesn't exactly work at the high molecular weight for this guy and doesn't work for the low molecular weight for this guy. Right. So something kind of wrong with it. Right. So what you can do is you can go back and say, instead of saying the stiffness, like LP would be kind of the stiffness, say the flexibility, which you 1 over LP. Then say the flexibility increases with the N groups, and then you get something that works. It's kind of weird. I mean, anyway, this is logical, kind of, except there's no reason why flexibility would be different than stiffness and why you would choose flexibility over stiffness. Right, except that we had, and you see in the literature that like they end up with this kind of function where the term of interest is this like lambda term, which is kind of a flexibility term. Right. So when they write these things out, this is like kind of the term that people use. So anyway, if you use that logic and just use an in-group analysis, you can get it to work. Like that looks kind of okay. This is for the Conley, this is for the Yithra, the guy who goes to the highest molecular weight, and then this is the Conley one somewhere here. So the Conley one still doesn't exactly work right. It works for the green, which is the high density branching. So I guess it doesn't work as well when the chains become more flexible, but who knows? That's kind of the deal here. Anyway, that's kind of the game, I guess, people are playing with. And then it changes with the branching positions, there's other functionalities that are introduced. And once you have the computer program running, you can do whatever you want. This shows that effect of like, if you have short chains, you get a lot more N group effect than if you have long chains, which kind of indicates it's an N group effect, you know, this molecular weight dependence. So I think that's all that's there, except those parameters could have some meaning, but like an infinite persistence. So that's that business. That was kind of like a trip down, looking at a few papers, you know, of not much importance. But then there's this business of the rotational angle for the and this is in that paper, right? It's got the 2 angles for the chain that he maps out in that paper for the homework. So anyway, so this is the traditional picture of this. It's in, so I got those books up here. So, oops, that's not what I wanted to do. It's nice to know that it does that. So this is in the book. This is in, I mean, this is in Florey's Florey 2 book, actually, but it's too hard to read there. Florey 1 is polymer chemistry. Florey biography. Maybe Florey 2 isn't here. Anyway, Florey 2 is a pretty complicated book. It's the one he won the Nobel Prize for. Florey 1 is the original polymer chemistry book from the 1960s. So every other polymer chemistry book is written after that book. That's a biography of the guy's life. Anyway, Fluorine 2 is covered in this book by Getty. Just kind of, it's a book I haven't really read completely, you know, but basically it's got this stuff in it. It says there what page? Page 24. So it's early on in this book. And it's just called Polymer Physics. Getty's a guy from Sweden or something, right? So I don't know who he is. But it's all right. So it's just a very traditional look at stuff. So here, this is Florey's second book he goes through. So it's kind of nice that he does that. If I could expand it bigger, it would be even better. It's really big. Weird about this thing. Anyway, so the idea is that you can kind of make a matrix. You have your chain index going one way. Let's see. You have your chain index going one way, chain index going the other way. So you're talking about binary interactions of the chain. This is kind of typical for polymer problems. So you have a polymer chain, looks like a thing. It has an index, might go from 1 to n, or he called it NB in that other paper, right? So you have that, and then you want to have like interactions of the different units of the chain. So you have like position 1 interacting with position 1. So you make a matrix. You want to know the interactions, and across this, those are all the 1 interactions, and then 2 with 1, and 3 with 1. And we said, like, before we had 1 over z plus 1, and then we take it to the n power, right, to get the effect of the. So you had your persistence length, and then the one that when you get to due to this neighboring factor thing, right? So you end up with a 1 over something to some power, right? So this is going to give you the power. So the power here would be like 2. This power would be like 3. This power would be 4. Whatever. So then, and it's a symmetric matrix. So this side is the same as that side. So you have to do it 1/2 of the time to get it, right? And you got to get, so this, everything you do with a polymer is going to end up being a matrix. And if you want to know, it's going to be matrix math. So that Florey 2 book is all matrix math. And it's all, and each of these arguments is going to be like some kind of energy function for what the rotation of a bond does to another bond. And it can be complicated, right? So, but basically the idea is the idea of this like 1 over z plus 1 thing to get the next step to the power is like the idea of it. So you could plug in any function you want for this, and then it's still going to be just to the power. And it's going to be the double sum across this matrix. All right, so Florey solved it. And again, he copied this guy Wolkenstein, who was a Russian, to do that. Who knows if he copied or not, but so there's the double sum, and this is the power. I end up with this power. Tau, it would be like your 109 bond angle for carbon. If you just want to consider the 109, then this one's like 72. So 180 minus 109 gives you the 72. It's this bond angle. So they talk about that bond angle as like theta, and then they get the 72 from the 180 minus. You know, it's just that thing to raise to this power n minus 1 as you go across this matrix. Right? So it's just matrix math. And then you can solve the chain every possible. So this function can be more complicated. This is just the rotational. So this is a freely jointed chain, means like he's only considering that he has this 109 bond angle, and this thing can rotate freely. We know that that rotation is hindered by this potential function that has to do with the rotation angle. Right, so it has that potential function you have to consider, which is complicated. So it'd be more complicated if you want to start to talk about the real chain. Anyway, so so he's got two angles after that, and but it's the same thing. It's the powers of that thing. So so this isn't done anymore. Like this was popular in 1962 or something, right? So and then Flory wrote that book, and in fact, in that book, he published every polymer. Then, like after that, his postdocs have published every other polymer that was ever invented. Right? So like it's already been done. There isn't much more to do. It's like you can use a computer to calculate, but it isn't really a simulation. Like you just do a calculation. What you get is the final, the chain structure. And you can get it because these rotations are temperature dependent. Then you can get that business as a function of temperature. And then once you can get it as a function of temperature, you can tell when it crystallizes and what the glass transition is. And also because you have the entire chain structure, you can Fourier transform it and get the diffraction pattern for the polymer. And it matches, like it matches perfectly. Right. So you could predict the melting point, the glass transition, and the diffraction pattern of like every polymer doing this matrix math thing. That was kind of what they said that he won a Nobel Prize for. And the real reason is kind of political, like the US needed a Nobel Prize. That guy was there, it had something to do with polymers. I mean, that seems to me like how this really works out, because there's a lot of smart people. You know, a lot of times, like DeGennes, I know the polymer one. So DeGennes won it for polymers for the reptation model. But actually, this guy named Sam Edwards in England that actually invented the reptation model, but he didn't even share it because England already had a Nobel Prize and France hadn't, so they got it, you know, kind of, pretty much. That's how it worked, you know. So anyway, there's a lot of smart people. Some of them get a Nobel Prize, some don't. None of us will get one. I can tell you that. Maybe, you know, it's possible, but I mean, the guy that just won it for the lithium ion battery, right? He's teaching at University of New York in Binghamton, which is, because he went there because like IBM is near there and they bought him at university almost. But basically, it's kind of odd, it seems, you know. Now New York is dumping a bunch of money into lithium batteries, so who knows? It seems to be political, whatever. Anyway, so that's Flory's Nobel stuff. I don't really want to, I'm not going to really go through it in detail. We could, you know, if you want to, it's in some detail here in this book. And then let's see. There's two other books here. So, well, actually, there's two other books on the webpage. You can read through it if you want. I don't want to, really, you know. That's kind of the basic thing. So Colby calls it the icing chain model. And it's on page 59 of Colby's book. So Colby's a guy pretty well known. 59, eh? So this is kind of the same thing, but calling it the icing chain model, you can see it's kind of the same thing. So everyone has the same thing in here. So he calls it the icing. So it's Flory called it the rotational isomeric state model, RISM, RASM. And then later on, two guys at Sandia, Curro and Schweitzer. Schweitzer's now at Illinois, and Curro retired. Developed the random something state model, also called RISM, which is a computer simulation. So it's a RISM computer simulation, and there's a RISM Flory Nobel Prize thing. So they changed their name to PRISM, the Polymer Random Something State Model. You know? So anyway, there's some problem with RISM. You might see RISM under two different contexts, and it might be called PRISM. Anyway, so he called it the icing model in here somewhere, because basically it's kind of like the icing model in the Monte Carlos thing is kind of an icing model. Okay, so the icing model is this thing where I mentioned before. We have a magnet So you have a grid. Usually you can make a 3D grid. Each one can be up or down. And they're originally magnetic spins. So, and then you do this Monte Carlo thing using the Metropolis method. So Metropolis is a person, Monte Carlo is a place, icing's a person. Okay, so like Metropolis sounds like it's a place, but it isn't. Anyway, so the thing is like the magnetic, it can like you can due to temperature, these things will randomize, right? Using that Monte Carlo, you can figure that out, and you can lower the temperature, and then it'll phase separate into a ferromagnet, right? So it can go from paramagnetic to ferromagnetic. The domains will line up at a low temperature, which is called the Curie temperature, right? And then so you can model. So that was the original math, and then that math was ported into every other field, kind of like liquid crystals, like a liquid crystal display. You can use an icing model to talk about how the directors of the molecules line up. And then you can do any kind of phase separation with that. So it's kind of like ported to everything else. It's a simple model. You can write a program to do this yourself pretty easily. You can download an app for your phone that does it too. I mean, you just Google icing model. But anyway, so this thing about the bond rotation can be done with an icing model also. It can do a simulation of the bonds and have the probability. And that's kind of like what those papers are. So he calls it the icing model in this book. Anyway, so somewhere in here, so he's going through the same thing in here, and the other one, run out of these. The other one that's in here, it's Jacobi, Getty, and there's Strobel. Strobel's the book that I originally used in this class. I like Strobel, but it's complicated. All of them are complicated. Oh, but I have run out of things now. Here, it's Strobel 57, where he goes through the same kind of thing. So anyway, this is kind of pointless. I'm just saying, like, if you want to read about it, it's in here, this stuff. The icing chain. So he's talking about the same potential in the context of that icing model. So it's the same. There's the potential thing to get the probability. And then anyway, you can look through this if you want. I'm not going to go through because this is kind of useless. I don't think you'll see this in a paper. Like not a paper. This, you won't see this stuff in a paper. This is a demonstration. This is a diffraction pattern. So a Q of 1 is something like 10 degrees, 5 to 10 degrees. So Q at 10 is like 100 degrees, 2 theta in a diffraction pattern. So this is the amorphous halo of polycarbonate. And the prediction is the line and the measurements of dots from the Flory-Rhizome model, rotational isomeric state model. Right, so it works pretty well. To do that, let's see. So anyway, that's the potential thing. Ethane symmetric, butane isn't, right? Because it's got this extra group. So when you rotate it around, here it's all hydrogens over each other, and then here it's like the methyl groups overlap, so you get transposition and Gauche plus, Gauche minus. And then for a polymer chain, it kind of acts like this. The CH3 becomes a polymer. And so the bottom line of this stuff is that if you just consider the 109 angle and don't consider this Gauche plus, Gauche minus trans business, so you can get this C infinity to go from 1 to 1.4. So we got, before when I did just the no back step, I got 1.25. So using this more complicated, the 109 degree bond angle, you can get 1.04. If you include the Gauche and trans business, you can get 3.4. The actual number is 6.7. So trying to approach 6.7. This is just for one bond though. This is just one bond. So if you include all the bonds, you can get 6.7. So it's kind of like the more complicated you put into the calculation, then you can get that number to match. That's kind of the idea. So that's that same picture. So that's all I'm going to say about the Flory, because it's complicated and it's not worth it, because there's no papers that you can find where anyone's doing anything with it now, because once you did it all, yeah, that's how the polymer works. Then you know that, then you don't need to calculate that again, I guess. So then it just becomes an exercise in a math technique that you probably aren't going to use again, right? Because, but you can look at it. I mean, it's there. It's in all the books. Anyway, so that's there's a couple other things to talk. I mean, there's a lot to talk about this short range thing, which seems to be insignificant. I mean, the significance is, we said that the energy of the chain is going to be this exponential. Oh, sorry. .cam. Well, we had exponential Boltzmann like E over KT, and an exponential of 3 R squared over NL squared. We equated those two arguments and got that the energy of the chain is KT. The energy is going to be KT R squared over NL squared. Like this is 3/2. Right, so we got that energy. So it depends on what N and L are, you know. So that, in other words, the first step of calculating about the chain is going to include like what is N. So it is not the chemical N. So knowing this step length thing is important to just any kind of thermodynamic calculation, because it's the base step of the thing, right? And also, it's also kind of, you're saying that this L unit is a 0, entropy is 0 for that unit. It doesn't have any conformational entropy, right? So basically, N is going to decide the entropy of the chain. So knowing the N properly is going to be important to any kind of thermodynamics understanding of what a chain does. So even though it seems kind of insignificant to talk about the details, having a grip on N turns out to be like the first thing you need to know. Without that, you can't really do anything. Anyway, so there's two ways to get this. There's two ways to get this thing. So one is to say the chain has these steps, and just say it's LK and there's NK of those steps. This is Kuhn, KUHN, right? This Swiss guy, Swiss rheologist. So this is rheology. He was a rheologist and he invented this model. Basically, it's the NL squared. Right. And this could also be called not freely jointed. This is just a completely free chain. It's a Kuhn chain. There's a name for it. In other words, these things can go, this is a universal joint. It can go any place. Right? So it can even backstep. So the Kuhn model isn't really very realistic, right? Another unrealistic model is this model, so the persistent chain model. So you end up that 2 times the persistence length is the Kuhn length. That's kind of the rule that you get, that you want to get. So this is just like what's it called? The gas atom motion, right? So you have a gas atom, it flies around the room. It's got they call it a persistence length that it has. It's got a certain length that it travels in a straight line. It's from kinetic theory gases. Wikipedia that you'll find they talk about a persistence length, and this is from like 1870, I think. And I don't know who the person was that invented kinetic theory gases. Someone famous, but I don't know who. Anyway, you can. So that idea is that the gas atom actually travels around however it wants, right? But you can think of it as having kind of a persistence to it. So you take that continuous path and put a tangent on it, And then you can talk about the dot product of the tangents gives you this kind of persistence length of the thing, right? So that's the general idea here. You're going to take some kind of squiggly line, then you're going to say it has a tangent somewhere. The tangent at that point is a derivative of R with respect to the index of the chain, S. So index goes from I to S. S is a continuous number, and I is like a finite step. Then if you want to know the end-to-end distance, integrate the tangents. All right, so basically this becomes, so then you could get something like this thing has a decay function. Okay, so I have so I define a correlation function. So I have my tangent at position 0, and then I have my dotted with my tangent at position S. So dot is the cosine times t squared, cosine of the angle between them, t squared. So if this equals that, cosine is 0, then that's 1, so it's just t squared at the 0, and the S is 0, right? It's going to have to be 1, just if you want the average of that. Then at some point it's going to go to 0. Like it's actually, it will never go to 0. But basically, it's going to approach 0. Exponentially will decay. Exponential of minus S. So S has units of length, and I have to get rid of the units because the argument exponential can't have units. So I divide by some number. That number is the persistence length. So so that's the definition of what a persistence length is. It's like a weighting factor for exponential decay. Okay, so this is the same thing if you look at like Beer's law. The thickness of the thing over the absorption coefficient or something. It's Beer's law, right? And that's called linear absorption. So this thing is actually that your change in this correlation thing, this thing, equals a correlation thing times, this by LP here. So it decays negatively. So the change in my thing depends how big the thing is. Same with absorption. The brighter the light, the bigger the decay. That's why it's called linear, because the change is linear in the thing. It's confusing because they call it a linear decay and it's an exponential function. Okay. But the reason is that the change in the thing is proportional to the thing. So when you bring that down here, it's d thing over thing gives you 1 of thing equals S divided by LP, the argument here, which is negative. And Beer's law is the same thing. So it's just like Beer's law kind of. So anyway, so you might wonder, like, why do they call things linear when they're exponential? You know, so that's the reason why. So anyway, if you want to get R squared, so the average of that R is going to be 0. I mean, this will end up being 0 if you have a bunch of different chains, right? They'll always end up being 0. So anyway, R squared is the first number that has any value. So you take the dot product of the two tangents. So you kind of break up the dot product in here that gave you the exponential decay into these two integrals over the entire chain. Finally, you get that it ends up being the integral of that thing, which is this linear decay. And then you'll end up with this kind of funky function when you do those integrals. So anyway, this function you see in these papers on persistence, it kind of describes what's the R squared in terms of this persistence length. If you have a Gaussian chain, because this function depended on a Gaussian chain. In other words, this is for a chain that can backtrack on itself. It's random, completely random. This thing's probably also for a Gaussian chain, but I don't see exactly where it is. But anyway, it's got this long function unless you say, so here L is the contour length, like LP times NP. That's the same contour length, or NK times LK. It's the same contour length. So that the extended length of the chain doesn't change with the two models, capital L. So here we have LK times L, and here if L goes to infinity, this term drops out. You just have 2LPL, or approaches infinity, and then the L's cancel here, and you have LK's 2LP. For a Gaussian chain that's infinitely long. So if it's not a Gaussian chain, not infinitely long, that's not true. Not necessarily true. Might be kind of true. Generally, this is just accepted. Right, that LK is 2LP. You can see that that function kind of showing up like in this Yithridge paper, he's got almost that same function here, that persistence length function. Strobel's got it here, like, so that functions in all these books. So anyway, so that's that business. So you can measure this persistence length of the Kuhn length, and if you do neutron scattering, so you take a chain. So you take a chain. So you're gonna take a melt, like polystyrene, that like, well, you can quench it, but basically you run it at room temperature. We had it at height at like 150, and you quench it down to room temperature, and then you throw in like one chain of deuterated polystyrene, which is, so per deuterated means instead of hydrogens you have deuterium, which just weighs twice as much as hydrogen, but it's got weighs twice as much, but it's got the same chemical behavior. Okay, so it turns out that so deuterium is used in NMR, IR, and neutron scattering. Like, okay, so per IR, like twice the mass means the vibration. So if you have a bell or a pendulum with a mass on this twice the mass, it's got half the frequency. Right, so you can use it to tag something to see interactions and things. You can follow one unit of a chain of a molecule in IR. IR, it's a mass. In NMR, it's a spin state. So deuterium doesn't. Hydrogen has this magnetic moment. Deuterium doesn't. So you can wash out you can just look at the hydrogens and then have the whole of the sample deuterium. And then kind of similar to that, so neutron scattering, there's a nuclear cross section, which is a number kind of like an index refraction, except we can go plus or minus. Okay, and the biggest difference between any two materials on that spectrum would be like looking at lead or like hydrogen with X-rays, is deuterium and hydrogen, even though they're chemically identical. So you can so it'd be like putting lead onto your molecule, with X-rays, but it has no like lead would have a huge effect, or it wouldn't even bond there, right? But deuterium has no effect. You could drink it. You can grow like deuterated rats and then take their blood, like look at deuterated blood. Really, people do that. So anyway, apparently it doesn't have any effect on you. You can just drink it. Anyway, so basically it has a slight effect on the like there's some thermodynamic thing, very slight, but basically none. So you can take the chains and throw them in there. Then you can see one chain in a melt. And in a melt, the chains act like they can cross each other. We'll talk about how that happens. Basically, they act like a Kuhn chain. And then you can see that you can get a measurement like this. So, and then you can see it's Gaussian, so it's power 2, and then it goes to power 1. And where the transition is, that's the length. Like it's a rod, and it becomes a random walk. The transition between that is this Kuhn length. You can just measure it. You can measure it there. If you get this in absolute intensity, you can also measure it from the 2 part, because the prefactor of that's going to be like the have to do with the step length somehow. I don't remember exactly how, but anyway, that shows maybe a little bit better that it transitions from 2 to 1, and you can get that point. So that's that. That's how you measure it. That's one way to measure it. In rheology, you can measure it with just by measuring basically the plateau modulus or something can give you the step length. Or you can get like we did. Actually, we did. Yeah, we had that plot here. So we had like plateau modulus G prime, and then that comes down. Then G double prime, this is power 1, that's power 2, goes up and then back up, right? And this guy goes up over here. There's another crossover, and that's kind of at like LP. That's got to do with two things, LP and the tube diameter, D. So it's like those two things but so you can kind of get the persistence length from that G prime, G double prime, omega log plot. Kind of get the persistence length there too. I mean, they think they can. Neutron scattering, you can see it. That's it. That's how you measure it, basically. You can measure it in scattering. You can get it kind of backdoor through rheology. So anyway, that's about it. Any questions or anything? Any stuff? Next, I'm going to mention like a little bit about polyelectrolytes, because the charging will make the persistence change. And then I'm going to talk about tube diameter and packing length, two other numbers that are around the same size for melts. You know. So let's just call it quits there, I guess, unless there's any question. So email me if you have questions on that homework.